physical problem. And since we have an additional boundary condition called a dynamic boundary condition here, remember we have a bottom wall freeze interface, we have a kinematic, okay, and here we have a dynamic. And what the dynamic boundary condition will tell us? Dynamic boundary, once you apply a dynamic boundary condition by using this phi, okay, into here, again partial square phi partial t square for this argument here, plus g partial phi partial y when y equal to 0 should be equal to 0. They will give you this equation. Okay, this is final equation you will get. Okay, once you apply a dynamic boundary condition. And this boundary condition, this equation we call this is a dispersion relation in a wave. Okay, what's the dispersion relation mean? Okay, in a wave, so there's always, okay, has a relationship connect our wave speed. This c is our wave speed. Okay, and lambda is our wave number. Okay, so we have this wave is a target with a c. Okay, since our boundary condition is, you can see here, our eta is what? This eta is xt epsilon, right? And then sine 2 pi over lambda, and then x minus dt, right? C is what? C is wave speed. Okay, this is wave speed. Okay, our wave will travel. You can see later, a time later, this wave will become like this. A time later, wave will become like this. Wave travel with the speed. Okay, the different time. Okay, and now this relationship, dispersion relation, you can see this relationship is a relation between our wave speed and lambda. Right, lambda. The rest of this is our height, right? There's our dip. This is the constant. All the rest is constant. Only unknown is what? C and lambda, right? C is lambda, C and lambda. So this relationship connect our wave speed and wave length. This is called the dispersion relation. So in the other meaning, physical meaning for this, for different lambda, we have a different speed. Well, right? For different lambda, we have a different speed. So with our wave with a different lambda, with different wavelengths, they will travel at different speed. And this actually will be followed by between our wave speed and so this is called dispersion relation. And this dispersion relation is very important in wave. Okay, every time you're talking about a wave, you always have the so-called dispersion relation, and this dispersion relation relate our wave speed and wave length. Okay, they have to satisfy by some equation, and this equation called dispersion relation. Okay, so this is we have this traveling wave. Okay, this is traveling wave. Okay, we have this traveling wave. Okay, and then we can solve the velocity potential once get the C1 and C2. C1 is here, C2 is here, and then so we know the velocity potential. Okay, and once we know the velocity potential, okay, we can solve our physical problem. Okay, so this is how do we solve this? Okay, we get more detail. Okay, by applying the boundary condition, we can get our dispersion relation. Okay, this is already written here. Okay, I think summarize here the rest of the equation here. This transparency here just guide you go through the detail. How to evaluate C1 and C2, and then how do you evaluate C2, and how do you get the dispersion relation. Okay, and we have a discussion here, okay, based on the dispersion relation. As you can see, this is our dispersion relation. This is our dispersion relation. Okay, without any assumption. Okay, only assumption is what? Small amplitude. Okay. Small amplitude, this amplitude is much smaller than lambda, and also this amplitude is much smaller than h. H is the height of water. Okay, and we can have the discussion here. Okay, under the small amplitude assumption, we have this dispersion relation. Okay, if you consider the deep liquid mean what the deep liquid mean? The liquid height. Okay, h is much greater than lambda. Okay, that's called a deep liquid wave. Okay, deep liquid wave. So we will compare with the so-called deep liquid wave. When the boundary wall here, and we have the surface H here, this H, okay, this H is much greater than this lambda. So it's deep, very deep wave. Okay, and this boundary is far away bound. So this lambda here is compared with this H. This H height is much greater than lambda. This is called deep one, deep wave. Vice versa, H much less than lambda for the shallow water. Okay, we have this kind of extreme condition. So under the deep liquid, H much greater than lambda. What happens here? Hypertension when H over lambda is much greater than 1, right? Because H is much greater than lambda. Hypertension here approach to 1. Okay, so our dispersion ratio reduced to what? C squared over GH equal to lambda over 2 pi H. So this is deep liquid wave. Okay, we have a H much greater than lambda, and lambda much greater than epsilon. Epsilon is amplitude. Okay, because we also assume it's a small amplitude, since we linearize the boundary condition by small amplitude assumption. And here we also impose additional conditions. Deep liquid wave H much greater than lambda, so we can simplify our dispersion relation into this. Okay, vice versa, we have the shallow water, shallow liquid. Shallow liquid means H is much less than lambda, and then when the hypertension for this, when this number H is much less than lambda, this hypertension of this value will be approximate as equal to 2 pi H over lambda. So if you replace this, become like this by using the shallow liquid wave, and this will be lambda, 2 pi H and 2 pi will be cancelled. Okay, and so here we have the C squared over GH equal to 1. Okay, if you apply this into here, right, and times this, giving this, so shallow liquid wave give us our C squared over GH is equal to 1. And our wave speed is no longer the function of lambda anymore. Okay, so lambda disappear in the dispersion relation. Okay, this is have a lambda. C is a function of lambda. This is all the wave. Okay, have the same speed with the C below wave speed. Okay, so this is shallow liquid wave. So under this lambda is much greater than H, and H is much greater than epsilon. We have this dispersion relation. Okay. So this is a complete dispersion relation by using the deep liquid, shallow liquid. So we have this. This is a complete dispersion relation. We have the C and the lambda. So this is a dispersion relation. Should follow this. This is a solid line. Should be represented by using this equation. Okay. So this when our shallow liquid wave, shallow liquid wave gives us C squared over GH is equal to 1. So this is 1 here. Okay. And then if the deep liquid wave will be approximated by is proportional to lambda, so this is dashed line like this. So the dashed line here will be very close to the deep liquid wave, and this solid line will be approach to so-called shallow liquid wave. So this is called dispersion. When wave propagate at different lambda and propagate at a different speed. We call this kind of phenomenon dispersion. Okay, so that's a liquid wave. Okay, and remember at the beginning we say we didn't consider the subtension, right? Subtension. Okay, so if you go back to here, since our assume our pressure outside this interface here is atmosphere pressure. And this atmosphere pressure is the same as the interface here. So P is equal to a constant, equal to a atmosphere pressure. So we can neglect this term, assume that P is a constant. However, when you have the liquid and air interface, we will generate so-called subtension. When you consider the subtension, this pressure, at interface is not equal. So So physical problem is right now is to modify or consider the surface tension. Okay. At the beginning here we have the surface weight. So P here, P1 and P2 here. Okay. This is P0 and this is equal to PATM. Okay. And then at the interface here, at the interface any point, at the beginning we assume this P equal to PATM equal to P1 is small from liquid side. Okay. However, this may not equal if you consider the surface tension. Okay? So, because any liquid and air interface here, if you have a curvature here, you will generate surface tension. Okay, so let's consider surface tension. Okay, I modify this. Okay, instead of assume this P is constant, and we would like to small modify this term here. Okay, so next we try to evaluate effect of surface tension. Okay, and this is our interface. Okay, we just take a section of our interface. And when you're using the free body diagram, you can see here. When I cut the interface here, cut the interface here, right? And I suppose have the surface tension sigma here. And with a small distance delta x away, our sigma will become evaluate the sigma plus partial sigma partial x times delta x, because this delta is different, right? From here to here. So our surface tension should change small due to our delta x according to the calculus. Okay, and this is interface. This is interface, right? And partial eta partial x, because on the interface all the equation, all the interface is y equal to eta. So this represents the partial eta partial x is what? It's this angle, right? Tangent of this angle, because this is the eta dx. Right? So this is the tangent of this angle. So as you can see here, if I cut a small piece here, I go to a free body diagram here. This is the body. I have a sigma here. I have sigma plus partial sigma, partial x, delta x. This is the distance of delta x. Okay? And here we have this angle theta 1. This theta 1 can be written as what? Tangent of what? So the tangent of this theta 1 will be equal to partial eta partial x, right? Because this is d eta, this is dx. Okay? So here is a partial eta partial x. So our force in the vertical direction, because all the pressure is normal direction, right? So we take this force, sigma is a surface tension force, times this tangent will give you this component of force. So this component of force will be sigma times what? Sigma times our partial eta partial x. Okay. And on the other end here, our surface tension is like this. And the angle here is what? Angle here can be written by using the calculus, partial eta partial x plus partial square eta partial x squared times dx. And this is contribution due to a change of the delta x. This angle should change to this angle. Right? The tangent of this angle should change to tangent of this angle. Okay, so this is this is angle, and this is tangent of this angle equal to this at this location. Again, our force and times this tangent give this component here. Okay, so this component and this component, one is upward, one is downward. So for the upward direction, okay, as you can see here, this is our pressure in the liquid side, the P here. This is outside of the pressure, okay, we call it atmosphere pressure, okay, P sub 0. So P minus P sub 0 is upward, right, in this direction. So this times our delta x give me the force. Pressure times area give me the force. The force is the upward direction force. Plus this force, this is the force. This is surface tension, and take this direction component, we can get this force will be equal minus this. This is a downward, okay, downwards here. Minus this should be equal to 0. Okay, so that's once I consider the surface tension, the surface due to the surface tension should be governed by this equation. Okay. Okay. And then what can we do? Since delta x is small number, right, and delta x times delta x is even smaller, so we can negate the second order term. Okay, and then only the first order term we have is what? What we have is a sigma times this partial. So this is this term here. Because all the should be have delta x, but everything is already divided by delta x. So this is p minus p sub 0, delta x is cancelled. So this is sigma times this term, okay? And then again, it's this term here, this term times this term, right? So give you this, delta x also cancel. And since our sigma is function of what? It's function of temperature only, right? Sigma is a subtension. Subtension is a flow property. Okay, flow property should only change with the time, should change with temperature. I'm sorry. Okay, subtension is only affected by temperature, but here we didn't consider any temperature difference. Okay, all the flow field is the same temperature, so partial sigma partial x should be equal to 0. So this term can be dropped. Okay, and so this term multiply this term give you this term, and this term multiply this term. This term can be dropped, and finally we have this term multiplied by this term because delta x times delta x is smaller, even smaller. Okay, and the first term here, sigma times partial phi partial x here, and minus this term should be cancelled, right? This multiplied by this will be the same as this, should be cancelled. So only term left is these two terms. Okay, so by consider subtension, what happened? Our pressure. This is pressure at the decrease side here, right? And compare with outside air atmosphere pressure. At the beginning, we assume it's the same, right? Previous time, at the beginning here, we assume this is atmosphere pressure, and this is constant is equal to this. Okay, that's at the beginning. Okay, we have all this relationship. Okay, but here we consider the subtension, our pressure here, and the pressure outside here. P sub 0 should have a difference. Difference is due to the subtension. Okay, and this subtension sigma times partial a dot square partial x squared give you the difference. Okay, between our pressure in decrease side and the pressure in air side. Okay, because subtension can sustain some kind of pressure difference. Okay, so this is the boundary condition. Instead of assume P equal to P sub 0, we have to assume, when you consider subtension, we have to assume this. Okay, once you realize this point, that we can modify our boundary condition. But because the previous side, what do we modify? We only modify here, right? This is the dynamic boundary condition. Assume this equal to 0, right? And this gives us a dispersion relationship. Okay, because as you can see here, we can have this dynamic boundary condition give us a dispersion ratio. So since right now we already modify our pressure here, so we can reconsider our dynamic boundary condition. So this is dynamic boundary condition. Okay, this is Gaussian equation. This is kinematic boundary condition. This is dynamic boundary. This is bottom wall boundary condition. Right? We have a previous equation look like this. And by assume what? By assume with a subtension here. Okay, with subtension here. So we have to evaluate partial P partial T, right? Partial P partial T. So under this subtension here, okay, we have this relationship. So P sub 0 is a constant. So partial P partial T, this will be equal to 0. Only term left is this term here. So here we have a partial P partial T should be equal to mass sigma partial square partial x square partial a dot partial T, right? And this is this relationship. Okay, and as you can see here, partial a dot partial T can be written as by using the our previous boundary condition. Partial a dot partial T is equal to partial b partial y. So we replace the partial a dot partial T become partial b partial y by using this kinematic boundary condition. Here. Okay. So only difference is what? Only difference is dynamic boundary condition. Instead of using this equal to 0, I have to using partial b partial T using this here. Okay, when we consider the subtension. Okay, 那我们考虑表面张力的时候，我们就要多这一项出来。Okay, the rest of the equation is the same. Okay, we have a Gaussian equation the same, kinetic bounding condition is the same, bottom wall bounding condition is the same. Okay, and this is dynamic bounding condition is different. Okay, we consider subtension. And remember, in the previous, we try to evaluate all this phi here. Do we use any? When we have this phi here, we're using the bottom wall bounding condition, and this what? This is a kinematic bounding condition, right? And we can have a C1, C2. So this phi, it can be determined from the bottom wall and kinematic. Since our bottom wall and kinematic didn't change, right? We didn't change our bottom wall and the kinematic bounding condition. We only change is this dynamic bounding condition. So our phi should be the same. There's no change. But our dispersion relationship will be different because of when you consider the subtension. Okay, so we only have to re-evaluate against what? Dispersion relationship. Okay, so here we try to do is, okay, under this pressure, okay, this is dynamic bounding condition. So these two bounding conditions stay the same, Gaussian equation stay the same. So our phi is still the same, right? Didn't change. Okay, the only thing you have to evaluate against by using this phi here. Okay, this phi here into this dynamic bounding condition. Okay, and try to find the so-called dispersion relation when we consider a subtension. Okay. Okay, so that's what we try to do is here. This is our phi, okay, and then we apply to this equation here, okay, and this is our new dispersion relation. So we have a sigma term here, additional sigma term here. Previous we only have this term multiplied by this term. We don't have this term equal to 1, right? And since we consider subtension here, so we have additional 1 plus this subtension term here. Okay, so this is due to the subtension. So our dispersion relation will be, okay, multiplied by this, due to the subtension. Okay, I think I will stop here, okay, since we are already over 1 minute, 2 minutes. And once we have considered subtension, our new dispersion relation look like this. And then we have the deep water, shallow water liquid, so we can have a discussion later. Again, on Thursday, this coming Thursday, we will make up 1 hour